Hello and welcome back. In this video, I want to discuss Ohm's law, which describes the relationship between something called resistance and the current that flows through a wire. Now it turns out that when electrons move through a wire, there are resistive forces that are exerted on these electrons, which limit their speed. We describe the effect of these forces with a quantity that's called the resistance. Now, for the most part, wires inside a circuit have a negligible resistance. However, it's sometimes desirable to have a very precise resistance between 2 points inside a circuit. And to achieve this, people who design circuits use something called a resistor. I have a picture of one shown down here. When we're working through problems, we denote the resistance with a capital letter R. And when we draw a circuit diagram, we denote the resistor with a zigzag line like I have shown here. The relationship between the current that flows through a resistor and the resistance of the resistor is described by Ohm's law. And what Ohm's law says is that the current that flows through a resistor is directly proportional to the voltage difference across the resistor and inversely proportional to the resistance of the resistor. In other words, the voltage that's lost across a resistor is equal to the current flowing through it times the resistance. Now, as always, whenever I introduce a new quantity like this, I like to step back and apply dimensional analysis to find the units of this new quantity. So, applying dimensional analysis to Ohm's law, we can see that the units of resistance are going to be equal to the units of volts divided by the units of current. So this is volts per ampere, and we describe this combination of units as an ohm, which is denoted with the capital Greek letter omega, which kind of looks like a horseshoe. At this point, I'd like to introduce an analogy which many students find useful to both visualize what's going on inside a circuit, as well as to gain a conceptual understanding. And the basic idea is that we can think of the current that flows through a circuit as being analogous to water flowing through pipes. And in this analogy, the current that flows through a wire is analogous to the flow of water through a pipe. The voltage difference which pushes the electrons in a wire is analogous to the pressure difference inside a pipe which pushes the water. And the resistance of a wire is analogous to the frictional forces which oppose the flow of the water through a pipe. And just like Ohm's law tells us that voltage is lost when current flows through a resistor, when water flows through a pipe, pressure is reduced by the frictional forces that oppose the motion or the flow of water through the pipe. At this point, I'd like to use that analogy to gain some kind of conceptual idea of what the resistance might depend on. So at this point, I'd like to look at two different questions. The first question asks, how do you think the frictional force that is created by a pipe will depend on the cross-sectional area of the pipe? So if I had two different pipes, let's say I have a pipe that's relatively small, and here I have a pipe that's really, really large. If we think about this, you can imagine that the frictional force of trying to push water through this narrow pipe is going to be greater than the frictional force that you feel when you try to push water through a very large pipe. So here we would say that the resistance of this smaller pipe is probably going to be larger than the resistance of this larger pipe. Similarly, the next question asks, how do you think the frictional force will depend on the length of the pipe? So hopefully this makes sense that if you have a relatively short pipe like this, it's going to have less friction than if you have a really, really long pipe, because the longer pipe has more surface that can rub up against the water and slow it down. And so it turns out that in an analogous way, the resistance of a wire is directly proportional to the length of the wire, so the longer a wire is, the greater the resistance of the wire, and it's inversely proportional to the cross-sectional area of a wire, so the thicker a wire is, the less resistance it has. And it's also proportional to this constant here. This is the Greek letter rho, the same letter we used before to describe the density of water. And in this case, this letter represents the resistivity of the material, and that basically just describes how well the material conducts electricity. So for something like a metal, which has a low resistance, it'll have a very small resistivity, whereas something that does not conduct electricity very well, like vinyl or Teflon or something like that, that'll have a very large resistivity. So let's go ahead and look at an example. This example says an incandescent light bulb is made with a tungsten filament. When plugged into a 120 volt outlet, 1.24 amps of current flow through the bulb. If the radius of the filament is 3 times 10 to the minus 6 meters, and the resistivity of tungsten is 5.6 times 10 to the minus 8 ohm meters, the question asks us to find what is the length of the filament. So the basic approach which we're going to use to solve this problem is we're first going to use Ohm's law to relate the resistance of the filament to the voltage across it and the current that's flowing through it. Once we know the resistance of the filament, we can then calculate its length using the formula for resistivity. So Ohm's law tells us that the voltage that's lost over a resistor is equal to the current that flows through it times the resistance. And this means that the resistance of the filament is going to be equal to the voltage drop across it divided by the current that's flowing through it. However, we also know that the voltage is going to be equal to, the resistance is equal to the resistivity times the length of the wire divided by its area. Since we're given the radius of the wire, we could write this as the length of the wire divided by pi times the radius of the wire squared. Since we know everything in this equation, except for the length of the wire, we can go ahead and solve for the length. So by doing this, we'll see that the length of the wire is equal to pi r squared times the voltage that's lost over the filament divided by the current that flows through the filament times the resistivity of the filament. And plugging all these numbers into a calculator, we can see that the length of the wire is going to be equal to 0.05 meters. Ohm's law tells us that the voltage decreases when current flows from one end of a resistor to the other end of the resistor. And since we know that the change in the electrostatic potential energy of a charge is equal to the charge times the difference in the voltage between 2 points, this means that the electrostatic potential energy of a charge decreases when it moves through a resistor. And this energy that's lost actually is converted into heat. So what happens is that when an electron moves through a wire, it exerts forces on the nuclei of these atoms, and this creates kinetic energy in these nuclei that manifests itself in the form of heat. And in fact, most electronic devices which generate heat use this phenomenon. So things like hair dryers, toaster ovens, stoves, all of these things work by running current through a resistive element to generate heat. Now, because the potential energy that's lost is equal to the charge that moves through a voltage difference times the voltage difference, the rate at which energy is lost is going to be equal to the rate at which charge moves through the voltage difference times the voltage difference. And since the rate the charge moves through something is called current, this is just equal to the current times the voltage difference over which the current flows, which we usually just call I times V. Now, one thing I should point out about this equation before moving on is that this equation always holds. It doesn't matter if we're dealing with resistors or some other circuit element, and it doesn't matter if the current's constant or the voltage is being held constant. We can always use this formula to calculate the power that's being lost in a circuit element. However, if we're dealing with a resistor, we can go a little bit further. So if I want to calculate the power that's lost in a resistor in terms of the current, I can use Ohm's law. So we know the power that's lost in anything is equal to the current that's flowing through it times the voltage difference between the two ends. Now, for a resistor, we know that the voltage difference across a resistor is equal to I times R. So if I plug that into this equation, I can see that the power that's lost inside a resistor is equal to I times R, or I squared times R. And this is a very useful formula which we use whenever we have a fixed current. So for example, if you have a device where you have a knob that you can control the current that's flowing through a resistor, this formula will tell you the power that's being lost in that resistor. Or if you're working through a homework problem and you're given the current, you can use this formula to calculate the power being lost in a resistor. Alternatively, we can use Ohm's law to rearrange this formula in terms of the voltage. So we have power that's lost in a device is equal to the current flowing through it times the voltage difference across it. And Ohm's law says that delta V is equal to I times R. So this means that the current that's flowing through a resistor is equal to the voltage difference across the resistor divided by R. So if I plug that into the equation for power, I can see the power that's lost in a resistor is equal to V squared divided by R. And again, this type of formula is useful if you've been given the voltage and you're asked to find the power that's being lost in a resistor, or if you're doing an experiment where you have a knob that allows you to adjust the voltage difference that's being applied to a resistor. So let's take a look at an example. This example says a small electric heater is used to heat a cold cup of coffee. The heater has a resistance of 15 ohms and it's plugged into a 120 volt socket. The question asks us to determine how long it will take to heat a half kilogram cup of coffee if it starts at 13 degrees Celsius and we're heating it up to 100 degrees Celsius. And we're told that the specific heat of the coffee is 4,186 joules per kilogram degrees Celsius. So the basic idea is that the energy that's lost in the resistor is going to be converted into heat. Therefore, the power that's being dissipated by the resistor, that's the rate that energy is being lost inside the resistor, is equal to the rate that heat is being added to the cup of coffee. Now, we know several different formulas for calculating the power that's lost inside a resistor. Since we're given the voltage across the resistor and the resistance of the resistor, we should use the formula V squared divided by R. Since this is equal to the rate that heat is being added to the cup of coffee, we should set this equal to the heat that's being added to the cup of coffee divided by delta T. And remember that the formula for the heat is equal to M times the specific heat times the change in temperature. So rearranging this to solve for delta T, we can see that delta T is going to be equal to the mass of the coffee times C times delta T, this is the change in temperature, and we're going to multiply that by the resistance of the heating element, and we'll divide it by the voltage squared. And if I plug all these numbers into a calculator, I can see that this is going to be equal to 190 seconds. So I think I'd like to end our discussion of Ohm's law here, and in the next video we'll discuss how you handle circuits that have more than one resistor.